particular video, I'll show you how to attack a few multiple choice questions here regarding fluid dynamics. So in this first one, it says the figure below shows for arrangement of pipes through which water flows smoothly towards the right, and it says the radii of the pipe sections indicated. So as you can see here, this is 2R, R, and 2R, and so on for 4 different diagrams. And it says in which arrangement is the network done on a unit of volume of water moving from left to right, 0, positive, and negative. So essentially, I think the easiest way to attack this is just to know that the network is changing kinetic energy, or the work kinetic energy theorem here. I'm going to apply this because I know that as the volume of water moves through these section pipes, it speeds up or slows down based on the cross section. Okay, so I'm going to go ahead and break this up. Network is equal to Kf minus Ki, Kf being 1/2 mvf squared minus Ki, Ki being 1/2 mvi squared. And then from here, I can really just pull out the 1/2 and the m. So really the only thing I'm going to look at is Vf and Vi. So what is the difference here in this parentheses? Okay, so what is Vf squared minus Vi squared? What will that give me? So let's go ahead and analyze all these different, or all 4 of these diagrams. So I try to draw to the best of my ability to scale here. So here, in diagram 1, the incoming velocity is just some v, okay? And then I know that as it goes into a narrow section of the pipe, its velocity will speed up. Okay, so I drew here v being longer and the variable v being larger. But then when it goes back into the second, or I should say third section here, the now cross section is the same as it was before, so the velocity will drop down to what it was to start. So as you can see here, you have a velocity v. While it sped up during this middle segment, it went back to its original velocity or speed here. So really, in this diagram, there is no change in v. If there's no change in v from start to finish, then there is no change in kinetic energy. Okay, let's move into the second diagram. Well, the second diagram here starts off really wide. So the cross-section area here is really wide. So v here is going to be small or slow. And as the pipe goes from left to right for this second diagram, it gets narrower and narrower. So I would say v keeps getting larger and larger, as you can see by my vector length and the variable itself. So as you can see here, the incoming speed is small, and then as it exits the pipe, it's really, really fast. So in this case, there is work done on the volume of water. Okay, so let's move on to the third one. The third one, once again, starts off similarly like diagram 1. It goes through the second segment, pretty much similar to diagram 1. So I'm just going to call that big V as well because it's going to speed up. However, the difference between diagram 1 and diagram 3 here is that the last portion here is a lot wider. Because it is a lot wider, the velocity is going to be smaller or slower compared to what it was in diagram 1. Okay, and then let's move on to diagram 4. Diagram 4 here starts off narrow, so the velocity is going to be really, really big. And then it goes through this Y portion, which seems like it's about the same width, right? It says here 3R, and this is 3R. So it's going to be the same cross-section as this 3R. So the V here is about the same. I just kind of copy and paste this arrow length, so I can try to keep it the same as much as possible here. And then last but not least, it's going to exit with the same cross-section, because the cross-section here is called R. That's also called R. So whatever V incoming, that would also have to be the same V exiting. So let's go ahead and answer this question. The first one says, what is the network done? Which pipe will generate 0 work? So in order to generate 0 work, you have to have the same velocity in and the same velocity out, because we're dealing with the same volume here. All right, so as you can see in the first diagram, as I stated earlier, V incoming is the same as V exiting, so there's no work done because the V's are the same, right? There's only work done if there's change in kinetic energy, aka change in speed. And then, so I'm going to go ahead and highlight that one. So there's no work done on that one because the V's on the left and on the far right are the same. And then likewise with diagram 4, the entry speed is large. Why it did slow down, but it exit at the same speed because it has the same cross section. So I'm going to say that 1 and 4 is 0 work. Now we're looking for one that's positive work. Well, in order to positive work, you have to be speeding up. Okay, so the only diagram that fits that one would be diagram 2. So the water flow coming in is slow, aka V is small, and then as it exits through this narrow portion, it speeds up. So V is large. A large number minus a small number is a positive value. So this one will be positive. And then last but not least, it asks which one is negative. So the one that's negative here is diagram 3. You have a larger speed coming in, but then you have a slower speed coming out, just based on the width of the cross section. This is 2r and this is 3r, r being the radius. So therefore, I would say that because it's slowed down, the work done by it is negative. Okay, all right, that's that for that one. Let's go ahead and do this one. So this one says a horizontal venturi tube shown below have 3 sections, and it wants us to figure out which of the following statement is true based on the reading. So for this one, as you can see, there's 33 different segments of pipe. So here I'm just going to start from left to right. So if I call this arrow V, I know in the middle portion, because the pipe got narrower, the velocity have to be, or the speed here would have to go faster. And then when it exits through this third segment's a lot wider, so the speed would have to slow down. So there's my V, and then there's my V. Okay, so the length of the arrow and then the size of the V itself. Hopefully that helps you visualize the stuff. So I know that as V speeds up, pressure goes down. They're inversely related. So therefore, in this particular diagram, the one with the highest pressure would require the one with the lowest speed. Okay, so P3 here would be greatest because it has the lowest speed. P1 would be second greatest because it has, the second fastest speed relative to the arrows I've drawn here. And then the most narrow section would have the largest speed, so therefore pressure would be lowest. So the proper ranking in this one I would pick is D. Okay. Here, if you want to use Bernoulli's function to justify it, you can. Here, I'm just going to go ahead and cross out H1 and H2, because if you draw your 0 reference point and draw it to the center of the pipe, H1, H2, and H3 are all the same. So all the H's cancel out, so which means rho, G, H just cancel out on both sides. So really you're left with just pressure plus 1/2 rho V1 square equals P2 plus 1/2 rho V2 square. Now, if you want to, you can solve for P2. If you want to just kind of stick with this diagram, it says P1, P2. So you can go from P1 to P2 and then P2 to P3 individually. So here, I just set up P1 to P2 for you. So to solve for P2, you just move 1/2 rho V2 squared to the left side. It was plus, you move it to the minus. Now you can go ahead and simplify this if you want to. All right, this is just a mathematic to prove it. So here, both these, the second and third term has 1/2 rho in common, so I just factored it out. So really, at the end of the day, you're just looking at the difference here between V1 squared and V2 squared. All right. So for example, if you're keeping up with just the conceptual math here, for example, if I start from the first left segment to the middle segment where it narrows down, well, V1 here, right, is small. Well, a small number square minus a bigger number, because as it enters the narrow segment, the V speeds up. A small number square minus a big number square will give you a negative number. Well, a negative number times rho times 1/2 gives you a negative number. Well, a negative number plus a positive number would give you a smaller positive number, which implies that P2 would have to drop because the velocity increased. So mathematically it also works out. Okay, so like I said earlier, I want to choose choice D. And then here's a diagram to help you visualize, just in case this stuff is not sticking with you. Again, if the fluid flows slow, it is high pressure. If it flows fast, it has a lower pressure. So they're inversely related. Okay, and then last but not least, if you want to, you can also think of Bernoulli's function like this. Well, this whole term on the left side is just a constant. Whatever it is, it has to remain the same. Okay, so if you can visualize this whole entire box, it's just some value, and it's a constant, we say. So therefore, really, you can analyze the right side. Okay? Well, the right side of the function, you have P2 and V2, right? The density of the fluid cannot change, so it remains the same throughout. So if it goes through a narrow section and V2 goes up, well, if this term goes up, what happens to the pressure in order to keep the number on the left the same? Well, if this term goes up, this term has to go down in order to get the same number back. So intuitively, if the velocity or the speed of a fluid speeds up, it also tells you that the pressure in that particular segment has to be dropping or decreasing. Okay, so conceptually, hopefully either one works for you. All right, so that's that. Last but not least of this video, it says here, water flows at a constant speed of 16 meters per second through a narrow section of the pipe. So here I have A1, V1, P1 here, and this is what is the speed of the water in the section of the pipe that has a radius is twice of the initial radius. So we go from narrow to some section that is wider that has twice the radius. So for this one, I'm just going to crack out this particular problem using the equation of continuity. Here it says A1 times the speed at segment 1 or cross section 1 must equal to the cross section area of portion 2 times the speed at that particular junction. So in this case, I'm just going to go ahead and expand A1. The area of a circle, or the cross section here, which is a circle, is just pi r square. R here being R1 on the left side to start. And then likewise, A2 on the right side, I've broken down to pi times R2 square. However, you notice that I highlighted R2 here. Well, the problem states that, I went ahead and crossed pi out, by the way, just it appears on both sides. The problem here states that R2 is twice as large. So twice would imply R2 is 2 times R1. But then don't forget to square it, right? So this is where you have to look at function and see if it's being square. The radius of the area is being square. So I want to use parentheses to indicate that I have to square everything. So R2 itself is 2 times R1. But that R term is being squared in the equation of an area. So 2 square will give you 4. R1 square is just R1 square. The left side hasn't done anything in the previous step. So as you can see, on the left side I have an R1 square. On the right side I also have an R1 square. So I'm going to go ahead and cancel both those terms out. So really I'm left with the statement V1 is equal to 4 V2. Well, to find V2, I'm just going to divide both sides by 4. Therefore, V1 is 16 because it's given, divided by 4. So 16 divided by 4 is 4. Okay, so just pay attention to functions, make sure you substitute correctly, and use parentheses when appropriate. All right, I hope that helps. Stay nerdy, don't be whack.